Our project is auditory imagery of speech and non-speech sounds. Auditory imagination, also known as auditory imagery, is the internal experience of sound without an external sound source. Research in this area is very important because it could help us learn more about memory and even help inform algorithms for brain-computer interfaces. Previous research on auditory imagery has shown that hearing and imagining a sound relies on similar neural correlates. Since we know that processing is different for human vocal sounds in perception, this may hold true for imagery as well. We decided to focus on 2 exemplars of 3 different categories of sounds. And we collected electroencephalography, or EEG, data while people listened to and imagined these sounds. EEG is a neuroimaging method that records the electrical potentials across a participant's scalp. Afterwards, we conducted pre-processing, such as filtering, to remove noise and behavioral artifacts. The figure to the right represents our region of interest, or ROI, which we used for our ANOVA analyses.
First, we analyze the event-related potentials, which are the brain's average change in voltage in response to a specific event. In this case, that event is a perception or imagination of a sound. These are the results from an electrode in the top center of the scalp. Using an ANOVA on the ROI, we found significant differences across all categories for perception in multiple different time windows, but we found fewer significant differences across categories for imagery. However, the differences were still apparent, just on a lower magnitude. Here you can see the differences for perception across the scalp using cluster statistics. The significantly different clusters of electrodes are marked in red. Cluster statistics works by finding groups of electrodes that share a similar positive or negative difference between categories and comparing them with random permutations of the dataset to get the cluster's relative significance. We found significant differences in clusters of electrodes for perception between speech versus artificial and speech versus animal. We also investigated our data using time-frequency analysis, which involves taking a Fourier transform of the data to convert it from the time domain to the frequency domain. We found significant differences in the alpha power for perception between speech versus animal, as well as for imagery between speech versus artificial.
We also utilized machine learning models to classify different types of perceived and imagined speech and non-speech sounds. We hoped that machine learning models would be able to pick up on the nuanced patterns not recognized using other analytic techniques. The classification models we focused on were LSTM, a recurrent neural network, and EEGNet, a convolutional neural network designed for feature extraction and classification of EEG data. EEGNet provides us with the highest accuracy scores of the models used, largely due to its architecture as an EEG-specific network that includes several well-known EEG feature extraction concepts, such as optimal spatial filtering and filter bank construction. It has also been determined that EEGNet performs better in context of limited training data compared to other standard models because of its compact size, which avoids overfitting.
For our EEGNet results, we visualized 2 scores, accuracy and AUC, along with variance across the 10 folds used for cross-validation. We see that there seems to be higher performance within perception for classification between human and non-human sounds than imagery, demonstrating that categorical differences are stronger in perception than imagery. They are also higher than baseline performances for all, demonstrating that there are categorical differences in both perception and imagery. For perception versus imagery, we train on perception and test on imagery. And here we see above baseline performance, indicating that there are shared neural correlates for speech and non-speech processing between perception and imagery. Although our ERP and time frequency results show less significant categorical differences for imagined sounds, our above baseline performance for machine learning models show that a data-driven approach is necessary to capture the fine detail in imagined sounds. Thank you very much for watching.